All right. So thanks for the introduction. Thanks for the opportunity to present at this great symposium. And so the work that I want to talk about is on a slightly smaller length scale, right? So we don't have spheres and lines to describe those. We have spheres and wave functions because we really treat quantum systems. And I want to start by actually thanking some of my collaborators on this project. So this work it started in Lawrence Livermore, so together with Alfredo Correa and Yosuke Kanai. And then as we started to implement things, then also Eric Drager helped us out to run on the high-performance computers in Lawrence Livermore. And then thanks to Victor Anisimov at NCSA, we were also able to run on Blue Waters really well. So he helped us a lot with that. Now the title of my talk has the word quantum electron dynamics in it. And I want to start by just using this image here to explain a little bit what I mean by that. As you can see here, this image is also thanks to David Zamorano at NCSA, who is part of the Blue Waters visualization team. So it's a really helpful resource if you want to visualize your data. These things are in place, and you can contact these people. So he made this nice image here. And what you see in this image actually brings you to quantum electron dynamics. So you'll see these yellow spheres here. Those are gold atoms in the image. And then you see a white projectile, as we call it. So that's why we put this little trajectory here. So the projectile is a proton, right, or a hydrogen atom, and that moves through this gold material. And at certain velocities of this projectile, the energies are high enough such that the proton directly excites electrons. So that means, and I'll talk a little bit about that on the next slide, but what that means for simulations is that traditional MD approaches don't capture this at all. Because all of those, I mean, classical MD as well as Born-Oppenheimer MD, which is DFT-based MD, all of these approaches make use of the Born-Oppenheimer approximation, right? And what Born-Oppenheimer approximation tells us is that the electrons are in their ground states at all times, right? Now that is not the case anymore if a very fast projectile moves through a material. It can excite electrons, they are not in their ground states anymore, and that is what we wanted to describe. Okay, so let me start by telling you a little bit about why that is important. So if you think of this example of a projectile moving through a metal, for example, that is something that is clearly relevant in, for example, in the wall material of a nuclear reactor, right? So protons hit this material and create radiation damage in there, and in order to understand that, we want to model this. It's also relevant in fusion applications, basically wherever you have fast ions flying around, which is also the case in solar cells, for example. If you put the solar cell on a satellite, or you have semiconductor electronics in a satellite, all these materials are exposed to radiation in space. Now, a little bit maybe more an earthbound application is surface adsorption. So if you think of a semiconductor surface, right? So the semiconductor may have a band gap of 1 or 2 electron volt, maybe in this area, and the surface adsorption energy. So if a molecule comes in and adsorbs on this surface, these energies can be on the order of a few electron volt, right? Larger than the band gap. So that means this adsorption energy can also directly go into electronic excitations, right? So even in certain surface adsorption cases, the Born-Oppenheimer approximation may not be valid, right? So in those cases, you need to treat excited electron dynamics, and that's what we wanted to do. Now, there are many applications, as I just told you, but in this talk, I'll focus on this radiation damage problem. And just in order to get you an idea of what we're interested in there, I put this figure down here. So what you see is on the y-axis is the so-called stopping power. And you can really envision that as a friction force, right? If a projectile and proton hits a material, it will experience friction, just because it loses energy to the material. Now, so that's the y-axis, this friction force. And then the x-axis is the velocity or the kinetic energy of the projectile. And you can see that this friction force now depends on this kinetic energy. And as you can see, that very slow projectiles mostly interact with the ionic system of the material, right? So they transfer the energy to the lattice, if you want. That is something that can be modeled with well, maybe classical MD or with DFT-based MD. And that has been done in the past. But as I told you before, those approaches cannot model electronic stopping. So that's the red curve here. For fast projectiles, that is even the dominant energy loss mechanism, if you want, right? And if you simulate this situation, if you simulate a projectile which has a large kinetic energy, using DFT-based MD, you would just get 0 electronic stopping, right? Instead of this red curve with the maximum and everything. Okay, so it was our goal to model that in a first principles approach. So that people looked at this in the past, both experimentally and with models, right, with theoretical models, and we wanted to do that in a first principle scheme. Okay. So how do we do that? So we decided to use a time-dependent density functional theory approach. Now, for those of you who are familiar with density functional theory, you'll probably recognize this Hamiltonian. So in density functional theory, you show that the electron density is your fundamental variable, if you want, and you don't have to work with the full many-body wave function. So that's the first step. You see this electron density n here as well as here. And then you make another approximation in some sense, or you rewrite the problem, I should say, by using Cohen-Sham equations. Now, those are these Cohen-Sham equations. And in time-dependent DFT, those are time-dependent. So you can see that the Cohen-Sham states have a time variable here, so those will depend on time. And then the external potential also becomes time-dependent. So if you think of a DFT scenario, the external potential is the Coulomb potential of the ions, right? And if you now think of the stopping problem, that's where we have the time dependence, because one of the ions, namely the projectile, moves through the material, so that's a time-dependent potential, right? Okay, so those are the equations that we want to solve. And now when people do TD-DFT, they oftentimes do this so-called linear response time-dependent DFT. So they look at spectra. They make a linear response approximation, and then they calculate spectra. That's not what we do in our code. Instead, we do the so-called real-time TD-DFT approach, and what that means is we simply time integrate these equations, right? So we start with some set of initial conditions, evaluate the Hamiltonian at this time, and then go time step by time step, we integrate the equations. Now, this will be difficult because the time steps that we can use will be very small. So electron dynamics happens on very short timescales. And it turns out that we can use time steps on the order of attoseconds, right? So that's very short. So that's a problem. And that's why, and in addition, we want to study large cells. As you just saw the stopping problem before, ideally we have a huge supercell and just one small projectile to not have some sort of interaction between different projectiles. And all of that makes it necessary to have a highly parallelized implementation. Okay, so now let's say we achieved that. We time integrate these equations, and what we can then do is we calculate forces at each time step just using the time-dependent density, and then we can update the positions of the atoms. And this entire approach is now not called Born-Oppenheimer molecular dynamics anymore. That is Ehrenfest, MD. Okay, so we implemented that into the QBox code, which is a plane wave density functional theory code. And then we ran this code, and this code was highly parallel for the DFT part. And now for our time-dependent DFT part, we could make use of the structure of the code, if you want, because we used, I maybe didn't really highlight that, so we used an explicit integration scheme, a Runge-Kutta integration scheme, and explicit means it is based on operations h psi. And these operations h psi were already well parallelized, right? So that helped us a lot in order to also get a well-parallelized time-dependent DFT. So we implemented this time-dependent DFT into QBox, and then we ran on 2 different high-performance computers. So I said before, the project started out in Livermore, so we ran on a machine there, and we ran on Sequoia, which is a 20 petaflop blue gene machine. And then now we also got access to Blue Waters, so we also made use of this machine. So that will be the red line is Sequoia, the blue line is Blue Waters in this scaling plot. And what you see in the scaling plot is the number of time steps per second that we can run as a function of the number of compute cores. And yeah, again, so red is Sequoia, blue is Blue Waters, and then the dashed line is ideal scaling, and the solid line are the scaling results that we got. Now, for a DFT code, those results are actually very good. DFT typically uses orthogonalization steps, and those parallelize very badly. So we found when we compared those curves to a DFT curve, we found that they even went down as a function of compute cores. The more cores we used, the timing got worse because of this orthogonalization. We don't need that in TD-DFT, right? So we could really improve the scaling and can run on Sequoia. I guess we run up to 1 million cores, and on Blue Waters we didn't get quite the entire machine, but we ran also on a large number of cores there. And then up here you see the cell that we used. So we used 1,500 gold atoms. And now that is relatively large for DFTs, maybe not super large, but large enough. But for time-dependent DFT, that's a pretty big cell. And what makes it even more complicated is we used a large number of valence electrons. So we had a total of 27,000 electrons. And that is only possible if you have machines like Blue Waters. Otherwise, you could not run these kind of things. OK, so you probably saw many of those figures during the conference. So this is what it looked like when I think that was for the biggest run that we ran on Blue Waters. So you see this cube architecture of the nodes there. And all the yellow ones are now our job as it runs on Blue Waters. As you can also see, we're not using these red nodes here. So those represent the GPU nodes. And that is a current issue with QBox. Yeah, you're shaking your head. So QBox does not run on GPUs at this point in time. And I don't think many DFT codes do. I have to say that. Maybe that is something to explore for the future. But at this point, we were already very happy to even use the large number of CPUs. OK, so now I want to show you some results in the last few minutes. OK, so on the next slide, I will have a movie. And we saw that movies can be tricky. So just to show you what you will hopefully see, I put these static images here. So what we describe is, like I said, we describe the electron dynamics on an attosecond timescale. So we have a time step, I think, of 0.3 attoseconds for these runs. The yellow spheres are the gold atoms, and then we start a hydrogen projectile on one end of the cell, and we move it through the cell as a function of time. And then we plot isosurfaces of electron densities. So those will be these red and blue isosurfaces. And just to be specific, so that's not the electron density at time t, but it's the difference of the electron density at time t with respect to the one at t equals 0. Just to not have this entire cell filled with stuff, even though nothing happens, right? If you just plot the difference, you see where actually things change. And so that's why we plotted the difference. And then the movie, so I should say that we're not necessarily interested just in having this movie, but we can actually extract physical quantities from these simulations. So we're, as I said before, we're interested in the stopping power, right? And the way the stopping power is defined is the gradient of the total electronic energy as a function of x being the position of the projectile as it moves through the cell, right? So this is a quantity that people measure in experiment. So we extract that from our simulations and we'll compare to experiment. So before I show you those results, let me just try to start this movie. And nothing happens. So where am I clicking to make it happen, maybe? OK, let's see. OK, it thinks it's running, apparently.
Use the blue water trick. Reboot.
Maybe.
You have the same problem.
I know, it's not my laptop. I can try.
Yeah.
Let's see if that solves it. If you mind rebooting. I nothing sometimes.
Nothing so much. Yes.
Is everything closed now? Okay. And there we go again. Okay. Let me just. Okay, let's see. Okay, apparently this time does not help. Well, anyways, you would see. Let's see, it was. I don't know why that happens. Okay, so as you see, right? So the projectile will move through the cell, and now what happens? It will excite these electrons, and then we extract these total energy changes as a function of x. Okay, and that is actually now the slide with these results. So we plot on the y-axis. We look at the stopping power of this material for a given projectile velocity. And what we see here is 3 curves. So the blue one, the blue solid line, is experiment. So for experiment, we use this, I put it up here, the TRIM database. So that's a database that is available online where people carried out many actual radiation experiments, right, where they put projectiles and put those on many different metals and non-metals and everything. And you can just access and download this data. So we use this blue curve as experimental reference. And then we compare so we calculate 2 different trajectories and compare to experiment. Now what you'll see is that both trajectories actually agree pretty well with experiment for low velocities. And then the black one starts to deviate more than the red one for high velocities. And from those simulations, we were able to actually explain why that happens. And what the reason behind that is simply that if the projectile moves, so the black one is a channeling trajectory, meaning the projectile moves just linearly on a channel like this, right? So there is a certain minimum distance that it has to some host atoms, if you want. Now, the red curve corresponds to a random trajectory. So we literally assign this projectile a random vector through the cell. So it can get very close to host atoms also. And we found that if that happens, the stopping power for fast projectiles is larger because when the projectile gets very close to host atoms, it can also excite core electrons, which it cannot if it's not approaching the host atoms closely enough. So that is what we could show relatively clearly from these simulations. So that's actually a good result. I don't think that was known before. Okay, so we can use these this code that we have now and really run well on blue waters. I guess that was the first message that I wanted to show you. And in addition, we get really good agreement with experiment. So at that point, I want to conclude. So using this example of stopping power, I hope I could convince you that this electron dynamics, excited electron dynamics, is important in several cases, and we specifically looked at the case for electronic stopping. And we can actually achieve a very accurate prediction or description from first principles. And this is only possible if we have this highly parallel implementation, because time steps are small, supersizes are big, so we cannot run on a tiny machine, basically. And then in the future, we hope that we can use this code to study maybe situations that have not much to do with stopping anymore, but things like surface absorption maybe, or photochemical reactions. So this coupling between excited electrons and lattice dynamics, if you want, that occurs in many instances. So I hope that we can use this code for many different exciting applications. Thanks.